And great. And screen sharing. Okay. So we'll have to go quickly and live light on the land in this lecture. So I wanted to discuss quickly the Liskov substitution principle here. Discussion in class suggested that perhaps there were some confusions about this. So the Liskov substitution principle is about how to use safe subtyping in the context of polymorphism, which is sort of the main attraction for many people to use subtyping. And we're going to be talking about a context where we're going to have a supertype C and a subtype of it called D. Now, these could be classes, but they needn't be. C could be, the supertype could be an interface, for example, that describes a certain contract, and D could be a class that implements that interface. Often, D is a subclass of C, but subclassing gives you subtyping. It also comes with other things like inheritance, which are different. But we're today going to be discussing the subtyping side. If time allows, in the remaining 5 lectures, we may get into, additionally, some aspects of subclassing that complicate the picture beyond the considerations covered here in subtyping. But the Liskov substitution principle is about safe subtyping in the presence of polymorphism. Meaning that if we're operating, we have code, for example, that takes in an object that adheres to type C, to the C interface, right? We call that its a parent type, and we use it here. But foo, as you're probably aware, in object-oriented languages, foo, while it takes a C, it can be passed a D, an instance of D, right? Because an instance of D, capital D, is a subtype of C. You can pass a D as if it were a C. So this call over here to foo on the right is passing something that's really a D. Its actual type is a D, as if it's a C. And from within foo, it's treated as a C. When the code of foo was written, D may not have even been a speck in the cosmic eye. It may not have been a type that was yet created. C may have been the type around, and D was created long after the code for foo was created. And we want to be able to safely pass here Ds as if they were Cs to code that relies on manipulating Cs. This is what the Liskov substitution is about. A principle is about how to do that safely. And this principle is key to recognizing a legitimate subtyping relationship, what's called a behavioral subtype relationship. Okay? The statement of principle is due to Barbara Liskov, one of my former professors, I'll note, who taught me, as well as Jeanette Wing, who was her doctoral student and later became the faculty chair for the computer science department at Carnegie Mellon. And the statement of the principle goes as follows. If we have a type T, this is a super type, and there's a property, Q of X, provable about objects of that type, of the super type. So in our case, it would be C back here. Then it should also be true for any object of a subtype of T. So if there's a property that you can count on about objects of type C, it should be something you can count on of objects of type D, is the idea. If foo is counting on things being true about Cs, the way they behave, they're invariants, they're history properties. the preconditions and postconditions for methods, what I can pass it as arguments to functions, what I expect back from it as return values, the exceptions that it can throw. If I'm counting on things about a C, just knowing that it's a C, they need to hold for any D's passed to me. That's the idea, okay? And I'm going to try to convey to you that this is a common sense notion. And it's not being picky. It's being sensible, okay? So Liskov substitution principle sometimes carries over mistakenly as a matter of being picayune about programming, being overly restrictive. But it's actually about preventing defects, preventing sometimes subtle defects, defects that occur perhaps when code is first written and when code is modified, and that are pernicious, particularly pernicious, okay? And it has to do with the fact that someone reading about the properties of C, if they're writing code against C, meaning using things of type C, all they know is that they are things that adhere to the contract for C. We don't want a D passed into this code to break it, for them not to be able to count on those properties. They need to be able to count on those same properties of C for anything passed in as if it were a C, like a D. Trying to make sure you get the intuition here. We're going to explore this with examples, okay? So if we have this code where the apparent type is C, the actual type is a D, D is being passed to foo as if it's a C. The actual type is D, and that's a subtype of C. To avoid the code, the risk that this code here has to change with every new D that's introduced, any new subtype of C. Any subtype needs to adhere to the behavioral guarantees, the assurances, precondition, postcondition, invariance, history properties, and the behavior you expect of this C. So the idea here is that, look, these types are providing contracts. They're providing assurances, things that the developers can count on who use them. So if I have a C, in instance, if I know I have a C, I am counting on certain characteristics of how it behaves. And anyone who uses objects of C is relying on those characteristics. Maybe they read about them in online help. Maybe they know about them through documentation from past work with this class, etc. More than that, anyone who's going to, not just users of it, like foo, who uses instances of this, anyone who's going to subtype this, anyone who's going to create a D that's a subtype of this, is going to be counting on those properties as well. Should be considering them, should be taking them into account in how to build the subtype. And not providing a clear specification of those properties is going to lead to guesswork that will almost inevitably lead to errors sometimes. So we're seeking here to introduce, to clearly communicate the contract. Okay, so I'm going to introduce a common sense example to help motivate this claim that I'm making, that this is a common sense notion. By the way, I notice this slide is not fitting in here, so I'm going to shrink it down in kind of a brutal way. Okay. Okay, so I'm going to be thinking about these contracts as service contracts of sorts. And I'm going to use an example of delivery services, okay? So if you consider how a company like Purolated Courier works, or FedEx. These are franchise operations. So you have the parent company, say FedEx, and then you have particular FedEx offices, which may be a store, which has other lines of business. But one of the services they offer is, as a FedEx franchise, they provide certain guarantees. So if you drop off a package by noon, then perhaps delivery is by noon for the parent company. Then maybe the parent company, say FedEx, provide a guarantee that it's delivered to Toronto by 5 p.m. the next day. So maybe this is a guarantee that FedEx as a whole provides. And if you set up a franchise for FedEx here in Saskatoon, you have certain rules of engagement of what you can change within that guarantee of FedEx. Someone may come to your franchise having read the rules for FedEx in general, right? The FedEx rules. And they see on the FedEx website that if you deliver your package by noon, it'll get to Toronto by 5 p.m. the next day. They see that on the website, and then they come to your franchise. They know there's a FedEx franchise around the corner, and they go to the FedEx franchise. Now, the FedEx franchise could adhere to that same guarantee of the parent company. Drop it off by noon, guaranteed to get by 5 p.m. to Toronto. That's perfectly fine, adhering to the same guarantees. But the FedEx franchise could be a little bit different in its guarantees in a certain structured way. There are certain things it can innovate around. For example, the franchise, if you know, based on the guarantees you can offer about the timing of flights from the Saskatoon airport or what have you, that in your franchise, you'll accept packages for drop off by 3 p.m. because you know there's a flight to Toronto by 4:30, and you can get your packages, as long as they're in by 3, you can get them to the airport and to ship. That's fine. You could offer that as a franchise. No one will be shocked. No one will be dismayed. No one will be rudely surprised if they check the FedEx website and it says you have to get it in by 12 noon, but you come to the franchise and they say, oh, for our franchise, we'll accept up to 3 because of the way the flight schedule works here in Saskatoon. That's fine. You can do that. You adhere to the rules for FedEx, but you provide some extra functionality within those rules. Right? So you can loosen the restriction. If someone gets it to you by noon, you have to get it. They would be rudely surprised if you can't get it to Toronto, but you can offer some additional flexibility. And similarly, if you know that you can get it before 5 p.m. the next day to Toronto, because you have Santa's, reindeer sled, and you can get to Toronto extra quick, or you have a corporate jet which will go off to Toronto, and get it to Toronto such that the package is delivered to the address in Toronto by noon tomorrow, that's fine too. You're living within the post conditions, within the guarantees of what FedEx offers, which is it needs to be delivered by 5 p.m. the next day. But you could deliver it sooner than that. But there are certain things you can't do, right? Like, someone will be really upset if they check the FedEx website and it says, get it into FedEx by noon, and it'll get delivered by 5 p.m. If they come in and you tell them at the franchise, hey, you're late. For our franchise, you have to get in by 9 a.m. They'd say, well, you're not FedEx. You're a fraud, right? You're not a real FedEx outlet. You're not providing the guarantees that FedEx provides. You're You're no FedEx. You're FraudX, right? And similarly for post conditions, if someone comes in having committed to going with FedEx instead of Purlator, and you come to the franchise and they say, oh, we take it to Toronto on dog sled. It'll be delivered by next year. That's our guarantee. Someone would say, that's not legit. That's not square. That's not according to the rules. So I'm imagining these franchises as kind of subtypes of FedEx. And my point of emphasizing this common sense example is that these subtypes are not restricted to only adhere to the exact guarantees of the supertype. They have the ability to change things in a certain legitimate way, in a way that is in accordance with delivering the service within the acceptable bounds that are guaranteed by the supertype. But there are things they can't do to change it. They can change it in certain ways and not others. Are we on board with this general idea? Okay, just leading you through some of the thinking, and we'll get to some computational examples here. There are several specific needs that comes from this. One of them that's very weak is signature compatibility. And this is a matter of what the signature is, what we take as parameters, what we return as return values, and the exceptions that we throw. We talked about exceptions last time. So, look, if you're in a subtype, you're in one of these subtypes, and you take parameters, and there's parameters taken by the supertype, and you take those parameters, you can take parameters that loosen the restrictions of what's imposed by the supertype. Parameters are the things you need to do a job. It's like you've loosened the time that someone must get a package in. You said, look, FedEx requires it by noon, but I'll give you extra flexibility. I'll take it until noon, of course, but I'll take it later than noon. I'll enlarge the possibilities. So when you have a parameter of a if you have a method in the supertype foo, okay, here we go. Just like the lottery again. Okay. We have foo, and it takes in a string here, O. This is in C, the supertype. Remember, we have a supertype and a subtype, D. Remember that? C has a method foo, which takes in a string. D's implementation of foo could take in the same string, right? It could take in a string, right? Oh, I said O. I'll call it V. So it could take in a string. That'll be fine. That'll be like the subtype allowing the package to be delivered or taken to the outlet by 12 noon. It can take the same expectation. But it could also accept something more than that. It could be more loose. It could accept it by 3 p.m. In other words, it could accept things that the supertype doesn't guarantee, but the subtype wishes to. Like it can allow it. It could take an object. That's fine. It needs to take strings, but it could take something more general than that. We call this contravariant. It's a term actually from category theory, but the point is D is a subtype of C. But the parameter here, object, is a supertype of string. Oh, thank you. That is Okay, I'm grateful. This is wow. Okay, that's great. Thank you. Thank you very much. At least it's Technicolor. Okay, so it's contravariant. Parameters for the parameters for a method in the subtype can take what's the types of the corresponding parameters in the supertype or supertypes thereof. Okay, so in the subtype, they can take parameters that are supertypes of what are taken in as the parameters of the supertype. So here we can take an object which is a supertype of string, even though D is a subtype of C. Yes, Connor. It's not extends. It's a supertype of it, right? Like a string is an object.
Oh, okay.
An object is not a string in general. So D is a subtype of C, but object is, I should have written it to be sort of, object is a supertype of string. So this can, in the subtype, we can relax the conditions. Again, it's just like in our FedEx franchise, we could take a package not only up till noon, that's guaranteed to all the guarantees that are required by the supertype, but we could be more loose than that. We could take objects. We can take things up till 3 p.m. As when they're delivered. These are the things we need to do our job. These are like the things that need to be provided to us. When the package is delivered to the franchise, we can be more loose. The parameter that's given to us, we can be more loose than the supertype. Do you get that? Now, for return types, we have covariance. The return type, if this method in the supertype returns if it returns an object, and I'm gonna try to figure out, if it returns an object, that method in the subtype could return an object. That's fine. It's like providing the same guarantees, like we get it by 5 p.m. to Toronto. But it could be more specific than that. It could provide tighter guarantees than that. Like it could say, hey, I return a string. That is an object. No one's going to be surprised. Someone who's calling the object foo based on the supertype is expecting any object. And the subtype saying, hey, I'm going to give you a string. Hey, that's an object. That's fine. You're not going to be surprised. You have to be ready to handle any object if you call foo, just knowing it's a C. If I get back a string, that's fine. Everything's cool. Just a type of object. But you'll notice that this is contrary. As you go down in subtypes, you could take more general things as parameters. But as you go down in subtypes, you can return increasingly tight subtypes. Or you could keep it the same, right? You could keep it as object. Do you understand that? And again, that's like the FedEx franchise. You have to guarantee it by 5 p.m. the next day. That's what the supertype does, the franchise, the FedEx in general. But you can be more strict or you can provide extra levels of guarantee, extra levels of specificity. I'm going to get it there by midnight with my Santa's sleigh. One fast sleigh, I'll tell you that. NORAD tracks it. Or I'm going to, I'll deliver it by 10 p.m. on the mark, on the nose. We can be more specific about the return type of a subtype. You get that? And the same thing is true for exception. Exceptions if this object foo can throw any runtime exception, the subtype could throw, it's fine if we want to say we'll throw any runtime exception. That will be fine. That'll be just adhering to the same guarantees of what could be expected. So someone counting as if it's a C, calling foo, knows they have to be able to handle any exception, any runtime exception. But in the subtype, we could be more specific than that. We could say we're going to throw a Stack Overflow exception or whatever, or divide by zero exception, divide by zero exception. And that would be more specific. That's fine. I mean, anyone who calls foo thinking it's a C should be able to handle any runtime exception, and we're just going to be more particular. We're going to be more specific. Just like we can be more specific about when we deliver the package consistent with the rules for the subtype. These things have to be some subtype of this. What the exceptions are thrown by the subtype have to be some subtype of the exceptions thrown by the corresponding method in the supertype. I'll try to post these online for those who are remote. The return values for the subtype, for the method and the subtype, are subtypes of the return values for the corresponding methods in the supertype. They could be the same, or any subtype. They're covariant. As we go down in subtypes, we can get successive subtyping of the return values and the exceptions, but the parameters, what we need to do our job, those can become supertypes successively. Just we can loosen the conditions of what we need. Is this coming across? Okay. Okay. So here, if I have a supertype and I have process string, right? It'll be perfectly legitimate, and it throws an exception 1. It returns a string. A legitimate subtype, a subtype that's perfectly legitimate, could implement that same method with exactly the same exceptions being thrown in its declaration, exactly the same return value and parameters. That's fine, right? That's just like our FedEx franchising, adhering exactly to what FedEx, the kind of guarantees FedEx makes in general for all franchises. Get it by noon to the FedEx to FedEx. We'll get it to the destination by 5 p.m. But we have more flexibilities than that. For example, we could take an object instead of a string. We can be more flexible with what's given to us. We'll handle more. We can allow delivery of the package up to 3 p.m. and throw an exception. Oh, we could throw an exception to subtype of that one up there. Right? But there are certain things we can't do. We can't have our subtype take a double instead of a string and call this process. No, someone will call process passing it a string, and if it gives a problem with the compiler because it's not a double, I mean that isn't fair and square. We can't say that we're going to return an object from the subtype where someone's expecting a string. Someone's expecting a string back based on the supertype. Who's writing code against the supertype, writing code as if it's an instance of the supertype. They expect a string back when we call process. We can't pass back any old object, right? Yes, Rob. So say that again. If it had this.
Yeah, so if you had like a method, a name that would return.
So right. So languages More advanced languages will accommodate these systematic changes. They will not accommodate something like taking a double as if it's a legitimate implementation of that method. But more advanced languages can allow you to take an object as the argument rather than a string, because it's a object is a super type of string. So you can, if all that the super type guarantees is it can handle a string, and you're saying I can handle any object, you're fine. But you can't say I'll handle only doubles, thank you very much, right? Because someone will be passing in a string expecting it's going to be fine, as if it's a super type instance, and suddenly it's going to say that's unacceptable for the subtype. That's a fraud of a subtype. Yes, Connor. Right. Yeah. So you need to distinguish. So this is a good question. You need to distinguish, though, two words. And I should have listened in the specifics of Rob's question. Rob was asking, what about, I think he said overload. Overloading is different from overriding. Overloading means you provide different definitions that can take different types. Overriding is what you do in an object-oriented context with a subtype versus a supertype. Here, my legitimate subtype 2 overrides process. You pass it at something that's secretly an instance of a subtype, as if it were an instance of my supertype. And if you call process, it's going to call the one on the actual one you passed, the actual type you passed. That's overriding. Overloading is providing several definitions that can take different things in them. And that's not an object-oriented notion. In fact, like in Julia, it's one of the main ways of sort of having language flexibility. And it's not particularly specific to subtyping. Subtyping is about overriding in subtypes. And this is going to become really important when we're talking about the behavior of these. Now, we're going to have to finish up quick. But the second, so I've been talking about sort of rules here. One is signature compatibility. That's what I focused on here. And there's this covariance contravariance distinction. For parameters, it's different from return values and exceptions. Parameters on the one hand, return values and exceptions in the other. Parameters vary contravariantly as you go down. The parameters go down the subtype hierarchy. The parameters can become more and more general, can become supertypes. For the return values and the exceptions, as you go down the subtype hierarchy, the return values and exceptions can be increasingly restrictive subtypes. That's fine. But the second thing is behavior. Subtype methods have to behave in a way that's consistent in terms of the post-conditions they guarantee with respect to their corresponding supertype methods. And here, in terms of behavior, the methods in the subtype can only weaken or maintain preconditions. They can accept more. Remember that notion for parameters? They can accept more things, right? Your FedEx franchise, you can take that package. If you have Santa's magic sled, you can take those. You could take something more general. You allow them to give it to your FedEx franchise by 3 p.m. No one's going to complain, you're a fraud. They're going to say, oh, wow, you provide all the FedEx guarantees. Sure, if I get it to you by noon, you'll get it to Toronto by 5 p.m. But you can do something better than that. You could take it by 3 p.m. and it'll be in Toronto by 12 midnight, right? So you can weaken the preconditions for the subtypes, for the methods and subtypes. You can strengthen or maintain the post condition. So you can be more specific within the bounds of what post conditions are guaranteed. You can be more specific. Instead of saying, I'll deliver it sometime before 5 p.m. the next day, you say, no, I'll deliver it by noon, by midnight. I'll deliver it in a restricted set of them. And it's the same basic idea for post-conditions and preconditions. You can weaken preconditions for the behavior of the subtype. You can handle more cases for the preconditions. And then post-conditions, I strengthen them. I can be more specific about what I guarantee, as long as it's consistent with within the rules of the supertype. Okay. And you have to be able to preserve provable properties. Now, we've talked about, for methods, preconditions and postconditions. But there's two other things, and we'll have to finish up talking about these next time, because time is just about out. But in the subtype, the supertype's invariants, things that are always true at any one point, like a field is always greater than 0. The size is never empty. Things that are true at any one point. You have to maintain those in the subtype. More than that, history properties, things that you compare what's true at time t1 and time later than t1, anything that's guaranteed for the supertype, like that a counter only rises, either stays the same or rises. That has to be maintained by the subtype as well. You can't change, for example, something that's immutable supertype, where it guarantees that it's always the same, into a subtype that's mutable. No, someone who's programming against an instance of the supertype, all they know is an instance of the supertype, or that it adheres to the supertype contract, may be counting on it being immutable. They may not check it again because they think it's always got to be the same. And if a subtype changes that, you could break their code. You can't, if the supertype only allows inserts, you can't have a subtype that suddenly has deletes, because you're breaking what they're counting on. They're once inserted, always present. So there's rules here. So we're out of time, and you've got to get back to Thorvaldsen or Arts or wherever. We're going to go through some examples of this. I think what I'm going to do is distribute some of them to you ahead of time. And I'll ask you to take a look at them, think about them, and then we'll talk about them. And I'll ask, are these legitimate subtypes? I'll give a supertype and then a subtype, and you'll tell me, is it legitimate or not, okay? And I want you to puzzle through it, and then we'll discuss it together, okay? I think I'll ask you to do it as a take-home exercise so you can get credit for it, with the goal being, it's okay to say you're not sure. I'm not going to mark you off for that, okay? I want you to struggle with it or grapple with it. And if you're not sure, just show that you've done some serious thinking about it, and we'll talk about the answers next time. Okay? We good? Okay. Good luck with ID 4, folks. And it's good to see you in person. Okay, thank you everyone online.